Everyone, I hope that you're all doing well. My name is Richard and welcome to Group Advanced Concepts presentation number 6. So a quick aside before we get started. This topic was a little confusing for me, so I'm going to do my best to walk through all of the information that I was able to gather. So with that out of the way, let's read the description. Aspirin was one of the first drugs to ever be produced. In the late 1890s, aspirin was discovered by Felix Hoffmann at Bayer in Germany. It wasn't until much later that we discovered the mechanism by which aspirin works. Today, there is a huge wealth of information available about how exactly aspirin inhibits cyclomonooxygenase, or COX. So our goals for this presentation. First, we are to investigate how aspirin works on both a pathway level and a mechanistic level. To be a little more specific, we're to walk through the pathway, including structures, metabolite names, enzymes, cofactors that aspirin inhibits. Also need to show the mechanism by which aspirin covalently inhibits COX. And for the second part, we know that aspirin inhibits prostaglandins from being formed, so we need to explain what prostaglandins do in respect to inflammation and how inhibiting their formation would reduce inflammation. So this is the pathway that aspirin inhibits. So the left is a little bit clearer. The image on the left is a little bit easier to comprehend than it is on the right. So you can see here that we start with a diacylglycerol or a phospholipid, and we either use the phospholipase C or phospholipase A2 to form the arachidonic acid, And we're more interested with this portion down here. So we're going to ignore the portion on the right here with the lipooxygenase. So we're going to look at the PGH2 synthase, COX1 or COX2, and peroxidase to form the prostaglandin, or PGH2. And then you can see there are multiple forms of prostaglandins here. You have PGD2 formed by PGD synthase. You have PGE2 and later PGF2 formed by the PGE synthase. You have the prostacyclin synthase forming the prostacyclin PGI2. And you have the thromboxane synthase forming the thromboxane TXA2, which we'll come back to in a little bit. So the arachidonic acid undergoes metabolism, as you can see here, by the cyclooxygenase enzyme and forms prostaglandins, which I mentioned earlier, which play a very important role in inflammation and pain. So of these prostaglandins here, the ones that have a vital role are the PGI2, PGF2, PGE2, and TXA2, as you can see here boxed in red. So let's focus on TXA2 for a moment. So this binds to a TXA2 receptor, and that's a GC-based G protein coupled receptor, and thus resulting in platelet aggregation, as you can see here. So how does this tie in with aspirin? So aspirin works by the acetylation of the serine residue in the cyclooxygenase enzyme, and it thus prevents the formation of prostaglandins, thus overcoming pain and inflammation. But at the same time, it also inhibits the formation of TXA2. So aspirin acts as an antiplatelet drug or antithrombotic drug, and thus it can be used in patients with, for example, cardiovascular disease. Because in cardiovascular disease, blood vessels are blocked by aggregates of platelets, thus resulting in a loss of oxygen supply to the heart. So this diagram here details how aspirin inhibits COX specifically. So again, like I mentioned earlier, the aspirin acetylates the serine amino acid residue present in the active site of cyclooxygenase enzyme, both 1 and 2 isoforms of the cyclooxygenase enzyme. And aspirin is mostly non-selective. However, it mostly inhibits the COX1 more than does the COX2, which is very important. So here's the structure of aspirin. And this structure is 15-HETE, which will come into play later. So just as an aside, the location of the serine residue in COX1 and COX2 varies. However, in COX1, serine is present in the 530th position and the 516th position in COX2. So you can see aspirin here. COX1, COX2 forms the salicylic acid, and as you can see, it's the COX1 that aspirin inactivates, which leads to an inhibition of prostaglandin synthesis. And as an aside, COX2 inhibits PGG2, but that produces this large molecule up here, 15-HETE, which is a new pathway resulting in the formation of leukotrienes, which are a form of leukocytes. So now let's get into prostaglandins and inflammation. So one of the functions of prostaglandins involves activation of the inflammatory response, production of pain and fever. When the tissues are damaged, white blood cells flood to the site to try to minimize tissue destruction. Prostaglandins are produced as a result. This is an example of a prostaglandin, by the way. So as I mentioned earlier, when you see that prostaglandins induce inflammation, pain, and fever, the first thing that should come to mind is aspirin. So aspirin blocks the cyclooxygenase enzyme COX-1 and COX-2, which is involved with the ring closure and addition of oxygen to arachidonic acid converting to prostaglandins. You can see here the blocking here. So the acetyl group on aspirin is hydrolyzed and then bonded to the alcohol group of serine as an ester. And what this does is this blocks the channel in the enzyme, and the arachidonic acid cannot enter the active site of the enzyme. So when you inhibit or block this enzyme, the synthesis of prostaglandin is blocked, which in turn relieves some of the effects of pain and fever. And again, also just as another aside, aspirin is also thought to inhibit the prostaglandin synthesis involved with unwanted blood clotting in coronary heart disease. At the same time, an injury while taking aspirin may cause more extensive bleeding. Thank you very much.